more pressure than what you're going to need for
Oh, God. Go right with that. Okay. If you have any questions about the test, you can see me either after class or before the next class, something like that. Okay, and I'll be glad to go over any questions that you have about the test. The average, I think I posted 84%, something was the average on the test. So it was I just consider that kind of a mid-B was the average, which isn't bad, really. And the median was 82%. I spent most of Saturday afternoon and evening grading this thing, and I have to tell you a story, which I'm sure won't interest some of you. But so then I go to bed shortly after finishing grading this marathon grading session, and so one of the nightmare that I had that night was this. I was taking a college algebra class, and I was also somehow or another the TA for the class, so I was taking it and the TA at the same time. Anyway, handing out these old, you guys don't know what mimeographed paper sheets look like, but anyway, they're terrible, usually terrible kind of copies. And so I get this, I'm now taking the test as a student, and it's like some complete foreign kind of algebra of I have no idea wherever that came from. Other students were finishing it, checking things off, and I was like, oh my gosh, I don't know at all what I'm doing. So that's what happened as a result of, it's not that you guys were like that, but that's what happened from grading right before you go to bed. All right? Okay. That homework number 11 is due a week from today. So we're going to continue talking about this, taking a curve and revolving it around an axis and getting the surface of the resulting shape. So what we're talking about is taking a curve like this. For instance, here's our y and x-axis, revolving it around, say, the x-axis, so we're going to get something down here that looks kind of like this, and we're revolving it around the x-axis to get a shape of some kind, all right? And we are then trying to find what is the area of the outer part of that shape. And you have this handout, I've got it lit up here on the screen also, that says if we're rotating about the x-axis, the general formula for the surface of this shape is 2 pi times y times ds, all right? And ds is that little infinitesimal length of the curve. That either equals this formula, 1 plus dy dx in parentheses squared times dx, or this, oh, I got to go over here for this thing, or ds is equal to 1 plus dx dy squared dy, all right? Which of those two we use depends on whether we're rotating about the x-axis depends on how our curve is given. And we're going to go through some examples with that. Now, say we are rotating this curve around the y-axis. So say we have something like this, and we're rotating it around the y-axis. Then on this side, we're going to have a mirror image like that, and it's going to be rotated around like this, and we're trying to find the surface area of that. And then with this, if it's rotated around the y-axis, the general formula then is 2 pi x times ds. And again, where ds can equal either one of those two formulas that I gave. And this is all given here on this handout that I've made up, area of a surface of revolution. Two main columns for this thing. The first column is if we're rotating the curve around the x-axis. The second column has to do if we're rotating it around the y-axis. Okay, these are the two general formulas for either one of those cases. Now, further down then, it depends on whether our curve is written as a function of x or as a function of y. So we have two individual cases for each of these. So if a curve is written as a function of x, we're going to use this formula for the ds. That involves the dy dx and the dx. If it's written as a function of y, we're going to use this formula for the ds, where it's dx dy squared dy. Okay. All right. So I think what we need to do here is just do a couple of examples here of this to see how this works. Because we never got to an example the last time. All right. So the first thing I want to look at is this. Say find the area of the surface obtained by rotating y equals the square root of 4 minus x squared under the radical. And this is for x going from -1 to +1. Okay, and we're rotating this around the x-axis. All right. So the general formula that we're going to use, because we're rotating it around the x-axis, is the one listed here, 2 pi y ds. So we're going to have the integral of 2 pi y ds. Since it is y in terms of x, we're going to use this formula for the ds. So we're going to have our ds here. Our ds will equal square root of 1 plus dy dx, quantity squared dx. And that's because our curve is y in terms of x. Now, we want to get everything in terms of x here. So I'm going to write here, I have got 2 pi, but now I need to write, instead, I'm not going to put y here, I'm going to put what y is equal to in terms of x, square root of 4 minus x squared, right? And then it's going to be times this 1 plus this dy dx squared dx. All right. So we've got to figure out what this radical ends up being so that we can do this antiderivative. So let's first of all get dy dx. All right. So our y up here is equal to 4 minus x squared raised to the 1/2 power. So its derivative then is going to be 1/2 times 4 minus x squared to the -1/2 power. And then we have to use the chain rule, so that's going to be times a minus 2x. So let me simplify this. We've got 2's that are going to cancel out, so I'm still left with a negative x, and then I'm just going to go on and put this in the denominator. It's a negative 1/2 power. I'm going to put it back as even as a radical over the square root of 4 minus x squared. Okay. So that's my dy dx. So now let's figure out what we have under the radical. So it's 1 plus the square of this. Well, what's going to be the square of this dy dx? Okay, well the top part is just going to be minus x times minus x, so that's going to be an x squared. The bottom part here is the square root times the square root, so that, oops, are we okay? So that's going to be 4 minus x squared. All right. Okay. So now we have to plug in, after the 1 plus, we have to plug in the square of that derivative, so I'm going to put in x squared over 4 minus x squared. All right, now all of the problems that you're going to be able to simplify what is underneath the radical to get something that you can actually get an antiderivative for. All right, so what the key to this is to get everything under the common denominator. My denominator here is 4 minus x squared. So I need to rewrite this. That 1 that I have there initially is going to be 4 minus x squared over 4 minus x squared. Get it over a common denominator. And then that's plus my x squared over 4 minus x squared. So I have it over a common denominator. So now I can combine those two terms. And what I get then is that the x squares cancel out on the top. So all I'm left with in the numerator when I add these two together is a 4, and the denominator is 4 minus x squared. All right. Now, since we have a nice perfect square on the numerator, I can simplify the square root of 4 as just 2 over, and then the square root of my denominator, 4 minus x squared. So I was able to do a lot of simplifying with that radical expression. So now let's go back up here to our antiderivative then. So it's antiderivative of 2 pi, and it was the square root of 4 minus x squared. And then we found that the radical then became 2 over the square root of 4 minus x squared. And this is dx. And now we do have to now put in our limits of integration here. We're told that x goes from -1 to +1. So in here then, I'm going to put in my limits, -1 to +1. Okay, well look at what cancels out in this integral. We have the square root of 4 minus x squared that cancels out. So what I'm left with then is just 2 pi times 2, or 4 pi, dx. All right, so I just have a number inside my integral, so I just tack on the x to it to get the antiderivative. So this is 4 pi x, and then I have my limits from -1 to 1. Okay? All right, so let's plug in our numbers. That's going to be 4 pi times 1 minus 4 pi times -1. All right. So that double negative becomes a positive, and my definite integral value is 8 pi. All right. So that's my area. Okay. You'll find that these integrals do simplify. Question on that first example. All right, let's go on then to another one. And here we're talking about, this time we're rotating it a curve around the y-axis. So here's the problem. Find the surface area of the curve y equal x squared rotated around the y-axis, and here it's for x for 1 less than or equal to x less than or equal to 2. All right. Now, it's not necessary really to draw a picture, but I'll do that here. Basically, y equals x squared is a parabola. So I'll just draw the right portion of it. And here we have x equal 1, x equal 2. So we're really talking about this curve right there, rotating that around the y-axis. So over on this side, we're going to get a mirror image that looks something like that. And it's going to be rotated around like that. And so the area that we're computing is the surface of that shape. Now, since we are rotating it around the y-axis, we're going to use the general formula, integral 2 pi x ds. So that's our formula, 2 pi x ds we're going to use. All right. Now here, we have y in terms of x again. So we're going to, since y is given in terms of x, we're going to use this form of the ds formula. ds is equal to the square root of 1 plus dy dx squared dx. All right. So let's figure out, first of all, what dy dx is, and that's easy. dy dx is just equal to 2x. So let's square that. So dy dx squared is 4x squared. All right. Okay, so therefore, ds then is going to equal the square root of 1 plus 4x squared dx, like that. And then let's go back to our entire formula right here. So therefore, we're going to have the integral. Now, our x goes from 1 to 2, so we put our limits there. And it's 2 pi x, and then I put my ds formula. Square root 1 plus 4x squared dx, like that. So now this is not a bad integral to get, antiderivative to get either, but what do we need to do here to obtain it? Yeah, a U substitution. Okay, is that where you're going?
I was thinking about last one.
Okay, all right, okay. Well, yes, Jen?
How come on the other we tend to plug in like the value of the y?
Okay, very good question. For the other one, when I was rotating it around the x-axis, okay, and our curve was given y equals a function of x, all right. Rotating it about the x, if our function is given like this, we're going to, if it's y equals a function of x, we're going to use this formula for ds in both cases. So here, the first case I gave, we're rotating it about the x-axis. Here we're rotating it about the y-axis. But in both cases, y is given as a function of x. So when y is given as a function of x, first of all, we use this formula for ds. Now, This is an integral with respect to x, right? It's dx. So, in this case, the general formula about the y-axis is 2 pi y ds. So I have to get some x's in there. I'm not going to keep it as y. So that's why I plugged in for y, I plugged in the x, what it's equal to in terms of x. All right, because I don't want to have two variables there in the integral. However, in the case that we have here, if I am rotating it about the y-axis, my formula is 2 pi x ds, because it's the radius of that circle. It's going to be an x. Since I already have an x, notice what I have here. Just keep as plain x. I don't have to do anything further with that part of it. I have the x there, I just keep it there. You see the difference? It's a little bit subtle, but okay, that's a good question. All right, so here we have it, and then Cassandra said let's do a u substitution. So what's our u going to equal, Cassandra? Right, 1 plus 4x squared, and then our du is going to be equal to 8x dx. And notice very nicely we have an x right here, so that's gonna save us with this. Basically, since we already have a 2x here, I'm just going to divide each side of this by 4. So I'm going to say 1/4 du is equal to 2x dx, because we already have a 2 there in our integral. All right, so let's look here at what we're going to get. Our 2x is going to be replaced by 1/4 du. I still have that pi there that I have to keep in, 1/4 pi. And then the square root is going to become the square root of u. And then we also have to worry about new limits of integration when we do changes of variable. So here, when x is equal to 1, our u is going to be equal to 1 plus 4, so it's going to be equal to 5. And when x is equal to 2, the upper limit, u is going to be what? U is equal to 1 plus 4 times 2 squared. So I think that becomes 17. So our new limits of integration using u then is going to be lower limit 5, upper limit 17. All right. So this is an easy antiderivative to get. We're going to have pi over 4. This is going to be u to the 3/2 power. And it's going to be divided by 3/2, but that's the same as just multiplying in front by 2/3. So pi over 4 times 2/3 times u to the 3/2, and we have our limits of integration 5 to 17. Okay, so simplifying, we can divide a 2 out from top and bottom there. So we get pi over 6. And then let me just use parentheses here. The top number is u to the 3/2 power, so just put 17 to the 3/2 power, and then minus the bottom limit's 5 to the 3/2 power, like that. All right? And then that's our answer. If you check some of these in the textbook, in the solutions in the back, I don't care that you do this or not, but they'll write like 17 to the 3/2 power as 17 times the square root of 17, all right? But I'm fine with just 17 to the 3/2 power, all right? So again, not to beat a dead horse, but I tend to do that anyway, is this. We have to be aware if we're rotating, first of all, about the x-axis or about the y-axis. And then in each of those cases, we have to be aware whether our curve is y written in terms of x or x written in terms of y. we'll get these two different formulas. They're similar, but they're written a little bit differently. And let's look at one more example here. Okay. Okay, now this example, we have it written as x in terms of y. So here's the problem. Find the area of the surface obtained by rotating x equal 2 plus 3y squared about or around the x-axis. Okay, and this is for y between 1 and 3. All right. So the first thing we want to look at is this. We're rotating this around the x-axis, so our general formula is the integral of 2 pi y ds. All right. Now, we're given x in terms of y. So we're going to use this formula here where we have the dx dy in our ds formula. So ds is we're going to use equals 1 square root of 1 plus dx dy squared times dy. Right? Okay, so let's figure out dx dy. So it's the same rules, except the variables are switched around to what we're used to seeing. 2 is going to go to 0, and we're going to get 6y. So dx dy is 6y. Therefore, dx dy squared is 36y squared. All right? Okay, therefore, ds is going to equal the square root of 1 plus 36y squared dy, like that. Okay, and now let's go to our general formula here. It's going to be the integral of 2 pi. Now here, notice now everything's in terms of y here. Here am I going to put something with x in it, or am I just going to put y as my next thing that I write? Just put the y. Right, 2 pi y times the square root of 1 plus 36y squared dy, like that. Okay. And now this is almost a carbon copy of the type of problem that we had. Oh, let me put the limits of integration here, 1 to 3. So this is just like the problem that we had before, where we're just going to put u is equal to 1 plus 36y squared and go from there. All right. du is going to be 72y. And so since we already have a 2y, I'll just divide by 36. So 1 over 36 du is equal to 2 times y. And then go from there. Our new limits of integration, let's see, when y is equal to 1, u is going to be equal to 1 plus 36, so it's going to be equal to 37. And when y is equal to 3, take my word for it that u is going to be equal to 325. Okay, all right. So therefore, we have our new limits from 37 to 325. And now let's see. Our 2y is going to be 1 over 36 du. Don't forget we have a pi there that I've got to keep. And then again, it's the square root of u. All right. So our antiderivative then is going to be pi over 36 times u to the 3/2 power. Again, dividing by 3/2 is like multiplying by 2/3. And I go from 37 to 325. Again, I can cancel out a 2 on the bottom here to get a 18. So I have pi over 54. And then the first term is going to be 325 to 325 to the 3/2 power minus 37 to the 3/2 power, like that. Okay? Just leave it like that. Okay. Let's see. Let me see something here. All right. And you see here, and the homework, and the homework instructions here, in particular for this section, I do tell you to watch out that for some of the problems you're rotating around the x-axis. For 3 other problems, you're rotating it around the y-axis. And then I have some hints here as to which DS formula to use. But it's all based on that handout. I think the one other thing that I'll go over in this is, let's see that. Here, just to point out some integration things. Here we're finding the area of this surface by rotating y equal e to the x power around the x-axis, so I'm going to underline that. And that's for x between 0 and 1, like that. All right. Basically, again, you don't really have to graph it, but it's going to look something like this. It goes up very quickly, and it's going to be rotated around like this. So it's going to be rotated around the x-axis. So because we're rotating it around the x-axis, then, our general formula is going to be the integral of 2 pi y ds. And we're going to use the ds equal to the, how about radical instead of integral? Radical 1 plus dy dx squared dx. We're going to use that one. Okay, well, the integral here, the derivative is easy to get. Well, dy dx is, again, just equal to e to the x power. So, therefore, dy dx squared is e to the x in parentheses squared. And what does that simplify to with exponential, according to the exponent rule? E to the 2x. We multiplied the exponents together. All right, so therefore the square root of 1 plus dy dx squared dx is going to equal the square root of 1 plus e to the 2x dx. All right, so basically the integral then that we get is going to be 2 pi. Now, am I going to put y here, or am I going to put e to the x? E to the x, because we're working with x. So 2 pi e to the x times the square root of 1 plus e to the 2x dx. And we're told our x's go from 0 to 1. Okay. Now, we see here this is going to end up being a little bit of a complicated antiderivative to get. We basically have to do like 2 different substitutions in order to get this. What might the first substitution be for u? The whole thing under the square root? I don't think that, if you do it, you'll find that won't work out very well.
You do well, not e to the 2x, but the power of 2x.
Just u equal to 2x, you mean?
Yeah.
Let's see, how would that work? Then, no, because then for e to the x, you would have e to the, what, u over 2? I don't know, Will, if that's going to do anything. How about just e to the x and see what happens? Nikesha's saying, yes, of course. All right, so let's look at u to the ex. All right. Du then, well, e to the derivative is just e to the x dx. And then what we end up with, so we have an e to the x dx right here. So that's going to be our du when we do the substitution. Now look at what we have underneath the radical. We have e to the 2x under the radical. Well, if u is equal to e to the x, then what is e to the 2x going to be equal to? Yeah, it's going to be u squared, squaring the e to the x. So when I do this substitution, let's see what we get here. The 2 pi is going to stick around. The e to the x dx, well, that all just becomes du. And then under the radical here, I have 1 plus u squared. We're going to have different limits of integration here when x is equal to 0, then u is going to be e to the 0 power, so that's equal to 1. And when x is equal to 1, u is going to be e to the 1 power, which is e. So our top limit then is going to be the number e. Ooh, I'm getting too far that way. Okay. So notice what we have here. This is a trig substitution then, where we use the tangent, all right? So I'm not going to spend much more time on this. I'm just going to say from this, we're just going to have to let u, this is our second substitution that we have to do. We're going to let u equal the tangent of theta. Because we have a plus here, we're going to use the tangent. So u is equal to the tangent of theta, all right? And then go from there. If, I'll say this, if you finish this problem, then I'll give you, I don't know. Yeah, I'll give you 5 points extra on the test, all right? So if you finish the formula, I'll give you 5 points on the test. So anyway, let's just leave it at that and go from there with it, okay? So you got the message out there. If you want to finish this thing up, I'll turn it in and then I'll do that. All right. By December the 9th. No. Turn it in by the end of this week.
Okay.
Turn it in by the end of this week. We don't want to delay this. We don't want to draw this out any longer than we have to. All right? All right. Okay. We just will be able just to get started with, so that's basically it with 8.2, this computing this surface area of revolving a curve. Section 8.3 has a couple of applications to it. In fact, here, let me get rid of this thing here, if I can. If it's going to let me. Ooh, oh no. Let's get rid of it. Let's put it down there. Section, here, and I can, for you guys, here. Do that, all right. Section 8.3, I'm only going to talk about one of the two applications, and if any of you are going to go into engineering, probably, I imagine either mechanical or civil engineering, this is something that you would see. This application is called moments and center of mass, or center of gravity. All right. And basically what we're doing here in this section is we're taking some kind of, say, thin plate of some kind, of some shape, and we're trying to see where on this I can put some kind of fulcrum, some kind of balancing thing, so that this whole plate will balance on this single point. All right? And we're going to assume that the plate it doesn't change in density. It's the same density throughout, so it has uniform density. All right. To get there, we need to kind of backtrack to, first of all, just the case where we're kind of looking at it like a seesaw type of thing. Let's look at two masses, two objects of some kind, attached to a very thin rod that's balanced on a fulcrum. I should have Googled that. I've heard that fulcrum, it's something that you kind of balance things on, but I didn't officially Google it. All right, so what we have here is we've got this thin rod. We've got a mass here, let's call it M1. We've got another mass here, M2, and maybe mass 1 is bigger, it's heavier. Basically, say this is heavier. For this thing to balance out, and you would just, this fulcrum would have to be closer to here for it to balance out, all right? Now, this second mass has a distance, we'll call it D2 from the fulcrum, and the first mass has a distance that we'll call D1. And there's an equation that must be met in order for this to balance. To balance, the first mass times its distance from the fulcrum has to equal the second mass times its distance from the fulcrum. Okay. So in other words, if a mass is heavier, then the distance has to be smaller. All right. And so any of you who've ever used a seesaw with someone, so then that's equally spaced, right? A seesaw. And so if you've ever used a seesaw with somebody who really outweighs you, then you know the problem of not being balanced. Let's put it that way, okay? All right, so we can kind of put this on an x-axis, put on, x-axis, all right? And we can, let's draw an x-y-axis here. So we have, say this is our first mass here, x1, at x1, and it has mass m1. And then over here we have at x2, at point x2, we have mass number 2. And let's say that right here is our center, where our fulcrum would balance it. We'll call this x bar. The difference between these two x's is our distance here. That's going to be x2 minus x bar. The distance here is going to be x bar minus x1. And so to satisfy that equation up there, we have to have m1 times x bar minus x1 equal m2 times x2 minus x bar, like that. All right. And we can do some algebra that I will omit to get this. We can solve for x bar, and we find out that x bar is equal to this, m1 times x1 plus m2 times x2 all over m1 plus m2. Okay, what do we have here? This is the sum of both of our masses. So this is the total mass in the bottom. Total mass. In the numerator here, this is called the moments of each x. The distance times its mass. So this is called the moments or the total moments. All right, and I tried to Google really what the why they ever started to call these things moments, you know, and I didn't really get a very satisfactory answer online. So, but that is what they're called. So it's basically distance times the mass is what it is. All right. Now, let's say we don't just have two masses, but say we have a series of masses, we can also find where its center point is. So basically, if we have more than two masses, we get this formula here. Again, this is our, shall we say, our center of mass right here, this x bar, and it's the same kind of formula. In the denominator, it's going to be the sum of all the masses. So say we have n of these, I'm just summing up all the masses in the bottom. So this is total mass. And in the numerator, we're summing up the masses times their distance. So another summation from j equals 1 to n of each mass times its distance, mi xi. And this would be the total moments. And that gives us our center of mass. Ooh, I think we'll leave, because if I even start to do 2 dimensions, it'll not happen in our time frame. So we'll just stop here at 1 dimension and finish this up then on Wednesday then. Did I give you back your? I think I mistaken. Just hand that back. Sure.
Like I can see now the limit comparison test, so that makes sense. But doing the ratio test showing that's inconclusive, and then doing the alternating series test, how's that wrong?
Okay, well, let's see here. We're trying to figure out absolutely conditionally convergent or, all right. Now, the alternating series test certainly tells us that it is convergent. All right. Now, the thing is, we want to know, well, is it possible it could be not only convergent, but absolutely convergent? So you decided to go to the ratio test. Now, unfortunately, the ratio test was inconclusive because it equals 1, which means that it tells you absolutely nothing. All right? So that's the thing. All that good work, unfortunately, tells us nothing. Okay? So the best thing to use here, and I know it's hard to keep all this stuff straight, the best thing to use for this kind of a formula is the limit comparison test. You use it with the divergent P-series.
I get it now.
Yeah.
Because this doesn't tell me
Cause this tells you nothing. I mean, it's a lot of nice work, but it doesn't tell you anything.
Sure,
Yeah, right.
that makes sense.
Uh-huh.
For some reason, I was thinking if I got one, it wasn't absolutely converted. But
No,
I mean,
there's nothing. Right. If you had gotten two, that's bigger than one, so it would have given you information instead. Right. Yeah, or if you'd gotten one half, but one, nothing.
Yeah, that makes sense.
Okay. This